Every year, tropical cyclones form over warm ocean waters, growing into giant spirals spanning hundreds of kilometers. They are weather systems so massive they can be seen clearly from orbit. When these storms make landfall, the destruction is absolute. In 1970, a single cyclone struck present-day Bangladesh, flooding the region and claiming an estimated 300,000 to 500,000 lives. Yet these systems begin as nothing more than a cluster of thunderstorms. The question is how rain clouds and warm seawater combine to create a planetary-scale force capable of wiping coastal cities off the map. Nature is the ultimate superpower, and we cannot negotiate with it. Our only method of survival is breaking down the atmospheric physics of how these enormous storms operate. Depending on where you live, you might hear this exact same weather phenomenon referred to by 3 different names. In the Atlantic and Northeast Pacific regions, they are called hurricanes. Across the Northwest Pacific, meteorologists call them typhoons. And when they form in the Indian Ocean or the South Pacific, they go by a third name, cyclones. These regional labels can be confusing, but they mask a simpler reality. No matter what the local populations call them, the entire globe is dealing with a single, unified physical engine. The recipe for a cyclone requires a specific environment. The oceans act as massive batteries, storing solar energy, and to jumpstart the storm, the surface water must heat up to at least 26.5 degrees Celsius. As the ocean heats up, water evaporates, transferring energy into the atmosphere. Huge columns of warm, moist air begin to rise. As this air lifts away from the ocean surface, it creates a deficit, a sharp drop in atmospheric pressure below. The atmosphere immediately attempts to equalize that pressure drop. Cooler, denser air from the surrounding environment rushes aggressively inward to fill the vacuum at the center of the storm. Because the Earth is rotating, this incoming air doesn't travel in a straight line. The Coriolis effect forces the wind to curve as it moves. In the northern hemisphere, this forces the massive cluster of thunderstorms to spin counterclockwise. Once fully formed, the anatomy of the storm presents a stark contrast. The center sits deceptively clear and calm in an area known as the eye, but immediately surrounding it is the eye wall, a dense ring of clouds holding the storm's most violent winds and heaviest rainfall. Powered by latent heat from the ocean and organized by planetary rotation, the cyclone operates as a giant, self-sustaining thermodynamic engine. While these storms threaten coastlines across the globe, the Indian subcontinent faces a unique level of risk. The Bay of Bengal routinely produces the deadliest cyclones in recorded history. The danger is baked into the geography. The coastlines of eastern India and Bangladesh converge to form a massive, shallow, V-shaped funnel. When a cyclone moves north through the bay, its extreme winds physically push the ocean surface ahead of it. Because the coastline narrows, that advancing water has nowhere to go but up, forcing a massive volume of the ocean onto the land. This is the storm surge. It overtakes low-lying terrain, destroys homes, and severely damages agriculture with saltwater intrusion. In major events, the surge is often deadlier than the extreme winds. The staggering historical death tolls in this basin are the result of severe meteorology being forced into a narrow geographic funnel, precisely where millions of people have built their homes. When a cyclone makes landfall, the immediate physical destruction quickly radiates outward into the economy. Ports shut down, agricultural yields are ruined, and factory closures delay global supply chains. While the tourism and insurance industries absorb massive losses, the aftermath demands a large-scale response. Rebuilding efforts drive sudden surges in construction, the building materials market, and disaster technology sectors. To manage these impacts, modern forecasting relies on a highly integrated web of early warning technology to track a storm's development days in advance. By gathering precise environmental data in the ocean, specialized buoys gather frontline intelligence. They constantly measure sea surface temperatures and detect the minute drops in atmospheric pressure that signal a forming storm. As the system approaches land, coastal Doppler radar arrays take over. These towers scan the incoming cloud structures to track the exact rainfall density and wind speeds right before landfall. We cannot diffuse the thermodynamic engine of a cyclone, but this extensive web of data collection buys emergency responders the single most valuable asset in disaster management: time. Forecasting bodies like the India Meteorological Department use this satellite and radar data to map out exactly where a storm will hit. This precision allows governments to execute massive preemptive evacuations. Evacuees are directed to purpose-built architecture. These multi-story reinforced cyclone shelters are elevated to keep thousands of people safe from a storm surge. Natural engineering provides another defense layer. Coastal mangrove forests act as a physical buffer, their thick roots absorbing wave energy before it hits inland settlements. Even with highly accurate warnings and fortified shelters, enduring a cyclone is a chaotic, punishing experience, defined by hours of extreme wind and torrential rain. This chart tracks cyclone fatalities over the past few decades. The data shows a clear shift. Where the 1999 Odisha supercyclone claimed thousands of lives, modern monitoring and evacuation protocols implemented during recent events, like Cyclone Fani, have dramatically flattened the curve. The physics of the atmosphere guarantee that these storms will continue to form, but armed with accurate data, resilient engineering, and coordinated planning, humanity has built a working system to survive them.